Good morning to all. In this session, we are going to see about the topic Smith chart and signal flow graph. So, Smith chart is a graphical aid that can be very useful for solving transmission problems. Although there are a number of other impedances and reflection coefficients charts that can be used for such problems, the Smith chart is probably the best known and most widely used. So, it is developed by 1939 by P. Smith at the Bell Telephone Laboratories. So the Smith chart is used to the design of single step and double step transmission line using the Smith chart. So for design of step, we can make use of the Smith chart. So the second most important point is it is used to calculate the length of the step, location, then standing wave ratios, then the RF of the transmission lines. Then third important point is Smith chart is used for impedance matching. So which plays a major role in RF circuit analysis. So it works on the concept of the quarter wave transformer. That means it deals with the transmission line where the length is lambda by 4. So in the quarter wave line, it insert in the input and output. So input and output impedances all equal. So signal is 100% sent with a maximum efficiency. The next one is it makes use of the maximum power transfer theorem where the source impedance is equal to the load impedance. So the reflection coefficient is the difference between the load impedance to the characteristics impedance. Then VSW or voltage standing wave ratio, which is the ratio of maximum voltage to minimum voltage of the signal. So this Smith chart will provide a very useful way of visualizing transmission line phenomenon without the need of a detailed numerical calculation. So this is how the Smith chart will looks like. So in the transmission line subject, you have learned how to calculate the reflection coefficients and VSWR in Smith chart. Whereas in case of the radio frequency, so the main thing is we can use a Smith chart for impedance matching purpose. So using the Smith chart, if a lossless line of characteristics impedance Z0 is terminated with a load impedance ZL, then the reflection coefficient, so this symbol is the reflection coefficient which can be written by Z of a load impedance minus 1 by load impedance plus 1. So which can be written as the reflect modulus of reflection coefficient e power j theta. So the same way, so we can able to write in the generalized the coefficient as z of in is equal to z naught 1 plus the reflection coefficient of e power minus 2j beta l by 1 minus gamma of e power minus j minus 2j beta l. So Smith chart can be also used for graphically solve the transmission line impedance equations. Options this can be written in terms of the generalized reflection coefficients. So here in RF, the major role is for impedance matching. To find the impedance matching, we can able to go for this Smith chart concepts. So the next topic is a signal flow graph. So the signal flow graph, the radio frequency signals are crucial in modern communication technology. So signal flow graph analysis is a powerful tool to optimize the system. So in radio frequency, that is a wireless communication. So the signal flow graph is a graphical representation of signal flow in a system. So they are used to analyze and optimize complex system. So signal flow graph are useful in identifying the bottlenecks and optimizing minimal path for maximum efficiency. So what is the benefits for a signal flow graph is identification of the signal flow issues in the circuit, then enables the accurate modeling of complex systems and it provides insight into the system performance. So this benefits make signal flow graph analysis a valuable tool for optimizing radio frequency systems. So the main application of the signal flow graph is the antenna placement, then signal routing and power distribution. It is used to minimize the interference and improves the system reliability. So the conclusion here is signal flow graph analysis is a powerful tool for optimizing the radio frequency system. So it provides a vulnerable insight into the system performance and enables accurate modeling of complex systems. So these are the benefit applications and conclusions of the signal flow graph. And the signal flow graph here you can see, so the primary component is the nodes and the branches. So node represents either a variable or a signal. So there are input node, output node and mixed node. So input node means only outgoing branches will be there. We can see in this diagram. The output node is only the incoming branches. Mixed node is it includes both the branches. So node represents a point which represents a variable or a signal. So in this graph, this A1, A2, B1, B2 represents the node. The branch is a line segment which it joins two nodes. So this S2, S1 and are representing the branches. So example here there are four branches. So now let us see how to draw a signal flow graph from a circuit. So it includes several steps. The first step is represent all the signals, variables, summing points, and takeoff point of block diagram as nodes in signal flow graph. It represents the blocks of a block diagram as branches in signal flow graph. So there are four rules which is associated with the decomposition of the signal flow graph. So the first one is the rule one is the series rule where two branches whose common node has only one incoming and one outgoing wave may be combined to form a single branch whose coefficient is a product of coefficients of the original branches. So these figures, so A represents this is a series rule and this one is a parallel rule. So we can able to draw like this. Next one is a self loop, so which consists of many nodes and branches. So the circuit can be replaced by this. And this the last one is the splitting rule, which is having the common point here in the V2. So this can be splitted like this. So the rule 2 is two branches from one common node to another common node may be combined into a single branch whose coefficient is the sum of coefficient of the original branches. So we can write V2 is equal to SAV1 plus SBV1, which is equal to SA plus SB into V1. So the third rule is the self loop rule. That is, when a node has a self loop of coefficient S, then self loop can be eliminated by multiplying the coefficient of the branches feeding by the node by 1 minus S. So we can write V3 equal to S of 3 2 S2 1 S matrix by 1 minus S of 2 2 into V1. So the last rule is the splitting rule. So a node may be split into two separate nodes as long as the resulting flow graph contain once and only once. So each combination of separate input and output branches so that connect to the original node. So we can observe that V4 equal to S of 4 2 into V2. So which can be written as S21 S of 4 2 into V1. So this can be explained with the help of this diagram. So here, this is a decomposition rule. The first rule is a series rule. Second is a parallel rule. This is a self loop rule. And the last one is a splitting rule. So after this signal flow graph, we can able to decompose like this. Okay. Thank you.